All right, so probability refers to the chance that an event will happen. So probability is represented as the ratio of the number of ways an event can occur relative to the number of possible outcomes. So we always put the number of favorable outcomes up on the top. So the number of ways an event can occur. So let's say we're looking for the probability of rolling a 1 or a 2 on a number cube. Well, you can get just that. You can get either a 1 or a 2, and then we would have 6 possibilities on the bottom. So basically I'd have 2 out of 6, or 1/3 as my probability. So the number that goes on top is the number that kind of is our favorable outcome over the total possible outcome. So example 1, if you roll a die, what's the probability of rolling a 4? Well, a 4, that's just one number, so we do 1/6. So there's one favorable outcome over 6 total outcomes, so 1/6. If you roll a die, what's the probability of rolling a number less than 4? So less than 4 would be 1, 2, and 3. So I'd have 3/6, which that equals 1/2. So I have 1/2 a chance to get a number less than 4. If you pick from a bag that contains 5 blue marbles, 2 green marbles, and 3 red marbles, what's the probability of picking a red marble? Well, there are 3 red marbles out of 10 marbles altogether. So if we go 5 plus 2, that's 7, plus 3 more is 10. So 3 out of 10. Okay, and that would be my total. All right, 3 out of 10. I can't simplify that. If you can simplify, you should always simplify your probability ratios. But 3 out of 10, we can't simplify that. Okay, so now probability of A and B. We're talking about independent events here. So if you flip a coin twice, what's the probability that heads comes up both times? So basically what you have to do is you got to figure out the probability of flipping a coin once. So we can get heads half the time. Now, the second flip would be, we also can get heads half the time. So this is like event A, and this is event B. So you got to figure out the probability of event A, the first event happening. Okay, and now we go ahead and multiply 1/2 times 1/2, and we're going to get 1/4. Because remember, we multiply straight across, so we get 1 times 1 and 2 times 2. So we should get heads 2 times in a row, 1 out of 4 times, or 1/4 of the time. We could also say that this is 0.25 or 25%, okay? Because we can list everything as a fraction decimal or a percent. So if we roll 2 dice, all right, what's the probability that a 4 comes up on both dice? Well, that'd be 1 out of 6 for the first dice, and then we get 1 out of 6 for the second die. And then 1 times 1 is 1, and 6 times 6 is 36. So we actually have a 1 out of 36 chance of getting a 4 to come up twice, okay? A standard deck of 52 cards has 13 card suits: diamonds, hearts, clubs, and spades. If the diamonds and hearts are red, and the clubs and spades are black, each 13-card suit contains cards numbered from 2 to 10, a jack, a queen, a king, and an ace. The jack, queen, and king are called face cards. So a game consists of drawing 2 cards, one at a time, with replacement. That is a very key word here. The fact that it says with replacement, okay, it is key that it tells us that. If it didn't say with replacement, then this would not be an independent event, okay? Because it would be dependent. Because if we drew a card, but then we kept the card, then we wouldn't have 52 cards in the deck anymore. We'd have 51 cards. So it changes the next probability. Okay, so, but if we draw 2 cards, but we draw it and then we put it back, then it remains the same probability, okay? So what is the probability of drawing 2 kings? Well, right away I have 4 kings out of 52 cards. Okay, and then remember I put it back. It says with replacement. So I multiply that by 4 kings out of 52 cards. Okay, and we're going to shuffle the deck, and we're not going to know what's going on each time. So it will be fair there. Um, now, one thing we can do is we can simplify these fractions here before we multiply. Okay, I can divide by 4 and get this to be 1. 52 divided by 4. Okay, well the 4 goes into the 5 once. All right, and there'll be 12 left over, so that'd be 13. Okay, which makes sense because, you know, there's 13 cards. It says 13 card suits. So then we gotta cancel out this other 4, make that a 1, and change the 52 to a 13. Okay, so then 1 times 1 is 1, and 13 times 13 is 169. All right, so as long as the deck is shuffled and you have an equal chance to grab any card on both draws, you have a 1 out of 169 chance of drawing 2 kings. Now, keep in mind, we did it with replacement, okay? So it was 4 over 52. Now, if we drew a king and then we didn't put a king back, remember, we would have only had 3 kings left, and there would only been 51 cards. So that would have changed the second one. But it says that we have replacement. So we just put it back and we use 4 out of 52 again. All right, in appreciation for the hard work, Kathy wrote 5 thank you cards and addressed 5 corresponding envelopes to her co-workers. However, by not paying attention, she randomly inserted the cards into envelopes and mailed them without checking the addresses. So what is the probability that all the cards were inserted into the correct envelopes? Okay, kind of a funny situation here, I guess. Well, first of all, we have 5 thank you cards, so I'm gonna make 5 lines. Okay, now obviously the first card that I put in to an envelope, I have 5 different ways of doing that. Okay, now after I put that card in the envelope, I only have 4 cards left, and then I'd have 3, and then I'd have 2, and then I'd have 1. Okay, so chances of getting that right, because, you know, think about the last problem. In this problem, we don't have replacement. Okay, so it's not like I put the card in the envelope and then I take it back out and then I have 5 cards to work with again. So once I put that card in, I only have 4 cards left. I'm not going to take it back out, so I wouldn't have 5 again. I'm not going to have 5, 5, 5, 5, 5. All right, it's going to be 5, and then I have only 4 left, and then 3 left, and then 2 left, and then 1 left. All right, now, so basically when I look at this, okay, I have a 1 out of 5 chance of getting that one right, and then I have a 1 out of 4 chance of getting that one right, a 1 out of 3, and a 1 out of 2, and then a 1 out of 1. Okay, and that's if I get them all right ahead of time. I'd have 1 out of 1. I'd have a 100% chance of getting the last one right if I got all of these right. Now, if we multiply all of these together, which is what we need to do, okay, so I'm going to put times, 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 okay, we could probably start to notice which one is going to work out, because 1 times 1 times 1 times 1 times 1, that just equals 1. And then without actually calculating it, I could say 5 times 4 times 3 times 2 times 1. So if I look here, I see that A is that choice. B goes 5 times 4 times 5 times 4 times 5, so that changes. And then 5 times 4, 4, 4, 4, 4, and then 5s. So this says we're going to take all the cards out after we put them in. So A represents what we're actually doing in this problem. Thomas is a set of 26 alphabet cards, so 26 letters in the alphabet, each having a different letter of the alphabet on it. He randomly draws 1 card and then rolls a fair die, numbered from 1 to 6. So what is the probability he draws a card with a vowel, A, E, I, O, and U? Now, I know we say sometimes Y, but this is not including that. It just tells us just to use these on it, and then he rolls an odd number. So we want the probability of drawing in a vowel and rolling an odd number. So we have 5 vowels there. So that's 5 out of 26 times, we want an odd number. Well, that'd be 3 out of 6, okay? Because our odd numbers would be 1, 3, and 5. All right, so now we can do some simplifying here before we get started. I could make this 3 a 1 and a 6 a 2. I can't simplify anything over here, so let's go ahead and multiply that out. We're going to get 5 over 52, and that would be my my answer. So 5 out of 52 is choice D. Okay. So again, we take the probability of one thing happening times the probability of another thing happening. All right, our last example for today, if the spinner above is spun 120 times, predict the number of times the spinner would land on section B. Now, first I got to take a look and make sure that all these sections are equal. As long as they are equal, okay, this would be kind of a 1 out of 4 chance right there. And this is a 1 out of 4 chance, okay, because they're all the same size. Okay, so it's important to determine your theoretical probabilities before we even start of each area. Okay, so we have 1 out of 4 chance for all of them. Now, if we're spinning it 120 times, we need to make a prediction. So I'm going to get 1 out of 4 times to land in section B. So now we are going to make a proportion equal to x over 120. All right. Now, you could notice a relationship between 4 and 120, or we can just cross multiply and then divide it out. So we'll go ahead and do that here. Whoops, clicked the wrong page. So I have 4x is equal to 120, and then let's divide both sides by 4. So I'm going to get x is equal to 30. Now remember, this is a prediction. So it says the spinner would land on section B exactly 30 times. Well, 30 matches, but we don't want it to say exactly. So the spinner would land on section B roughly 30 times, but probably not exactly 30 times. So that's the choice we're looking for right there. Because this is a prediction, so we can't say it's going to land on exactly 30 times. It'd be great if we knew that, but we just don't. So there's our day 2 probability lesson. So hopefully that helps us understand some of those question types.